Hey guys, Mr. Hedrick back here to discuss our next lesson on exponential and logarithmic functions, a continuation of the several units that we've been talking about this now. And we're going to enter into solving equations for the next couple of videos, and we're going to start with solving exponential functions or equations and then move into our next video where we'll talk about logarithmic. We've talked in the past about how to solve radical equations. It's going to be a very similar process as we're approaching exponential and logarithmic. So there's two different ways that you can approach solving these types of equations. One is algebraic, the other one is graphing. We're going to start with algebraic first, since that's what you've seen since Algebra 1 at least, and then we'll move into graphing and how that's a useful method to double check your work. So to solve equations algebraically, we're still going to be using the idea of opposite operations to eventually isolate whatever variable we have on one side of our equation and move everything else to the other side. So how are we going to do that in this case for exponents? The first thing that we're going to want to try to do is isolate the base and exponent that we're given on one side of an equation. Okay, so anything that's not part of that base, not part of that exponent, we're going to move to the other side of the equation. Then we'll rewrite from exponential to logarithmic form. Remember, the base stays the same, everything else switches. That's going to allow us to isolate the variable that we have, after which we can, if needed, approximate or round our solutions. If you get a decimal, this would happen. If not, you don't have to worry about this step. And lastly, to double check our problem, we're going to graph both sides of our starting equation separately and see where the graphs intersect. Something very similar to what we talked about with radicals earlier on in a previous unit. We're going to do the same thing here, and I'll have an example of that. A couple of notes before we begin. We will have to use the change of base formula, so I did discuss this in my last video. If you missed that, go check that out. We will use it here as we're solving again. And then if we ever have the special base e, remember that's like a special number, somewhat similar to pi. We are going to, when we rewrite our problem from exponential to logarithmic form, turn e into the natural log. So again, we'll have another example of this as we go along. And I already have an example set up here of these different steps worked out already. We'll see one where I work it out by hand, but we start with an exponential equation at the top here, and the first thing we're going to do, once again, is to isolate the base and exponent, in this case on the left side of our equation. So we have 4 to the power of x plus 2. 4 is the base, x plus 2 is the exponent. That -7 is on the same side of the equation as this base and exponent. We want to get rid of it. Move that -7 over to the other side, add it, cancels out, right? 57 plus 7 is 64, and now we have a base and exponent by itself. What does this allow us to do? It allows us to, step 2, rewrite our equation from exponential to logarithmic form. The base stays the same. 4 was the base, it stays the base. Now it's the base of a logarithm. And everything else switches sides. This parentheses, this exponent moves from the left side to the right side, the whole thing, and 64 moves from the right to the left side, now also part of that logarithm. Okay. And notice that this is where we would actually use that change of base formula, right? We have log base 4, a specific base of 64. In order to avoid complications with a calculator, what we're going to do here is say base b, bottom b of a logarithm division problem, and log of 64 over log of 4 equals 3. You can check that in a calculator, but this expression right here equals a 3. Okay, so 3 equals x plus 2. And finally, to get x by itself, of course, we have to subtract 2 to both sides. 3 minus 2 is just 1. And that would be the solution to our exponential equation algebraically. So that's following those steps. We're going to do that again shortly. But before we do that, I want to go over how you can double check this graphically. Okay, we talked about this in, again, a previous unit. If we graph the left side of the original equation and graph the right side of the original equation, setting both sides equal to y separately in a Desmos calculator, for example, the graphing calculator. We're going to look to see, do the graphs cross? Now we have to be careful here. Sometimes you have to zoom out to see whether they really do or don't. But if you zoom out and they do cross somewhere, that x-coordinate will be a solution. Okay? Versus if they don't intersect or they don't cross, then there's no solution to the equation. So in this case, we started with an equation, right? If we take that left side, 4 to the power of x plus 2 minus 7, set that equal to y and graph it. Separately, graph y equals the right side, 57. The graphs will cross. Now you will have to zoom out and zoom to see this, zoom out in Desmos to see this, but they will cross at the x-coordinate of 1. So this is a way that you can double check or verify that the algebraic solution that you found is correct. Graphing, solving algebraically, both confirm that you have the same solution to your problem. If you take that 1 and plug it back into your original problem, both sides will balance. Both sides will equal if you simplify both sides. Okay, so let's do an example that I have not already worked out, and let's make this one the special base e so you can see how that one would work. In this case, you will want to subtract by 2 at the very beginning, and in this case get something equal to 6. Okay. And you have e to the power of x minus 4 all by itself now on the left side of your equation. We've isolated our base and exponent on the left. That was step 1. Okay. Step 2, we're going to want to rewrite our equation from an exponent to a logarithm. Now this is where you have that special case where if e is the base, e is a special base, it gets a special logarithm. The natural log ln, lowercase l. Everything else still switches sides. So it'd be like natural log of 6. 6 moves from the right to the left side. X minus 4 moves from the left to the right side. And that allows us to, of course, in step 3 here, get x by itself by adding 4 to both sides. Okay. So if you went and typed this in the calculator, it will give you a decimal. I don't quite remember what this decimal is, but this would be one where you would need to approximate or round. So what I challenge you to do is go into the calculator, type in or look for the function natural log of 6 plus 4. It is a decimal. It could be something like 5.79 or something like that if I remember correctly, but double check that. And then whatever that decimal is, right, it's some decimal, go back and graph both sides of this original equation. So this is 5, your double check method, graph y equals e to the power of x minus 4 plus 2, and graph y equals the right side, which is 8. Where those graphs intersect should have the same x-coordinate as whatever the decimal is that you find from solving algebraically. Okay, so that would be how you solve algebraically, and then double check yourself always by graphing your two sides of the equation as well. One more thing I wanted to discuss before I ended this video was word problems. So nothing to be scared of here. We're still going to follow the same process as we've just discussed, depending on the problem that we're given, of course. But let's say that a scientist collects a bacteria sample and it begins with 8 million microbes. And then the sample size triples every 30 minutes. We're going to say that this equation matches this scenario. And actually we're going to prove this shortly. The first thing I want to do is to rewrite my equation to solve for t. How would I get t, time, by itself on one side of my equation? Okay. Remember, opposite operations first. So this is one, by the way, that you could not just graph immediately. Y equals y doesn't mean anything. So this is one where you do need to know how to solve algebraically or rewrite things algebraically. But we want to get the simple base and exponent by itself. 2 is the base. T divided by 30 is the exponent. We want to get rid of the 8. Okay? In this case, we're going to need to divide by 8 to both sides in order to get the base and exponent by itself. So this is like question number 1 here. We're going to come back to question number 2 shortly. Okay. First thing we did was divide by 8. Second thing that we're going to need to do is to rewrite our problem. So remember, the base stays the same. Base here is a 2. Now it's the base of a logarithm. All these other fractions are going to switch sides, right? T divided by 30 moves from the right side to the left. Y divided by 8 moves from the left side to the right. And lastly, to get t by itself, of course, opposite operations yet again. Opposite of division will be multiply. 30 to both sides. So in essence, what we're going to get is time equals, the time it takes to triple will equal 30 times this logarithm. Now, how is this useful? Well, let's say I want to find a specific number of microbes, right? How long will it take, right? We're trying to find t here. How long? We're looking for t, so we're already set up to do that. How long will it take for the sample size to reach 24 million microbes? This is like question number 2 that we're going to do over here. Okay. Well, 24 million microbes will be our final value that we're looking for. That will equal y in this case. Okay, so whereas 8 million was represented by an 8, 24 million is going to be represented by a 24. What we'll do is to rewrite what we just found and plug in that number for y. Log base 2 of 24 million over 8 million. Okay, and oops. So this is incorrect equation. My fault. This should be a 3 here throughout our problem. We're tripling, we're not doubling. So pretend that this base was a 3 the entire time. Small correction there. Okay, good thing I caught that. If we're tripling, we should have a base of 3. If we're doubling, we should have a base of 2. So keyword there would be triples. But I'll be giving you this type of equation in future problems, so you won't have to worry about that. Anyway, to solve this equation as it's given now, which is the correct version of this equation, what we'd want to do is the change of base formula. So think about, we have base b, bottom b, base is 3, that goes on the bottom of a logarithm division problem, and whatever's in the parentheses goes on top. Okay. Now 24 divided by 8 is just 3. It's like log base 3 over log, log 3 over log 3. We just simplified 24 divided by 8 equals 3. And anything divided by itself, of course, is a 1, right? This is going to equal 1. So, what does this mean? It means that we just simplified this portion, right? And we found that it equals a 1. So t equals 30 times 1, and that's just 30 minutes. Okay, what does that mean? It takes 30 minutes for the sample size to reach 24 million microbes. Now this makes sense if you go back and look at our original problem. It says that the sample size triples every 30 minutes. Well, what is triple of 8? The triple of 8 is 24. It should take 30 minutes for it to triple in size. Now, obviously, you need to write the equation correctly at the very beginning when you're modeling things and then solving from there. But otherwise, this does make sense. It takes 30 minutes for it to become 24 million microbes because 24 million is triple of the original 8 million. So this is one type of word problem or real-world example where mathematical modeling and solving with exponential equations can be very useful. We're going to move into our next video by looking at some different types of problems involving logarithms and how to solve those, word problems, and more abstract. Also, we'll be able to use graphing there. So I will look forward to seeing you then.